Thank you. And thanks for the opportunity to tell you a little bit about Summit and our Center for Accelerated Application Readiness. This is our effort to get applications ready for our next machine. It's a really exciting time because Summit at the moment is being built as we speak. And so Titan is our current platform, still the largest machine in the country, but soon we will have Summit, which will be 8 to 10 times faster. So we're part of the Leadership Class Computing Facility. This is a facility that consists of two sites, Oak Ridge Leadership Class Computing Facility and the Argonne Leadership Computing Facility. At Oak Ridge, we have fielded large machines for open science for the Department of Energy. Our previous machines were Jaguar. Currently we have Titan. Titan is a 27 petaflop machine, and it's based upon an AMD processor and NVIDIA GPU. So this is when we started to do accelerated computing. And we're currently building Summit. Summit is going to be up to 10 times more powerful in terms of applications than Titan is. It's again a hybrid GPU-CPU machine. And I'll say a little bit about that in a few minutes. We're never standing still, and we're actually already working towards what we call OLCF 5, the process of getting the replacement of Summit. So for us, it's a continuing replacement of machines. As I said, it's very exciting right now because we are building Summit as we speak. So this is a photograph of the as yet empty racks that we put on the floor. It takes a long time to prepare a facility for a big machine like this. Over the last 3 months or so, these cabinets have arrived. They're all being put in place. They're all being connected to power, to cooling. This is a water-cooled machine. And of course the network. And the network is already completely in place. This is a Mellanox full-fat tree InfiniBand, and you see on the top here the yellow cable bar. That's where all the cables go for the network. And I've been told we have close to 200 miles of fiber optic cable in this one room. So it's quite an undertaking to put this all together. So a few comparisons between Titan, our current machine, and Summit, as it will be available to the user programs in about a year. That's the time it takes to put this thing together, do all the testing, and making sure everything works correctly for our user programs. A few major changes. Currently, we have over 18,000 nodes on Titan. And this will actually go down to about 4,600 nodes. And this is really exciting because that means that these nodes are going to be tremendously powerful compared to what we have on Titan. The node performance will go from less than 1.5 teraflops per node to well over 40 teraflops per node. The memory per node is going up dramatically as well. Currently we have 32 gigabytes of memory with 6 gigabytes on the GPU. We will go to half a terabyte of main memory per node and 96 gigabytes of high bandwidth memory combined on the GPUs. This is for a lot of applications a really big deal because having more memory on the node makes your applications a lot more efficient. Something new that we will get is NVRAM, non-volatile memory on the node. And we go from having none to 1,600 gigabytes per node. So this can be used as a burst buffer to bleed off data that needs to go onto the file system. But there are other uses that we're investigating as well. Pre-staging of data for jobs, for example, or just temporary storage while a simulation is ongoing. Total system memory goes from 710 terabytes to over 10 petabytes on the entire machine. So this is going to be a really large machine. Our system interconnect goes from the Cray Gemini on Titan, which is a Cray machine, to a dual rail EDR InfiniBand from Mellanox. Currently we have one CPU and one GPU per node. This will go to 2 Power 9 CPUs and 6 Volta GPUs. You undoubtedly have had a number of talks about the Voltas, how powerful they are. We're going to get almost 28,000 of those on Summit. So this is a really great workhorse. And then, of course, the file system. And all of this with a modest increase in the power required to run this system. So the Volta, you've heard undoubtedly a lot about already. We will have this on NVLink and NVLink 2, leading to a double precision of 7.8 teraflops per GPU. We can do single precision, and it also has a tensor core on the Volta, so for deep learning applications this is a great resource to have. And an aggregate bandwidth on NVLink of 300 gigabytes per second. It's a great improvement over what we have now on a PCI Express bus. So we don't have this machine yet, and we need to prepare us for that next machine. Our applications, our users, our software developers. And so we have an early access system in the form of what we call SummitDev. It's for development. This is a Power8 prime processor, 2 processors per node, so 2 sockets, with 4 Pascal GPUs on NVLink 1. So this is an architecture that is way more similar to what we will have on Summit compared to what we have on Titan currently. And so this is for the software developers that make their applications ready for Summit, a great resource to have. Of course, this was also a new machine, and we got a lot of new software on this machine. And so here are just a few quotes from the teams that are working on this machine in terms of their experience using it. Now, in general, it has been relatively easy for folks that are already running on Titan to move to this machine, because you can just run multiple MPI ranks, each connected to one of the GPUs, and it should work relatively similar to what we have on Titan. Of course, it has a lot more capabilities, and that is what we want to explore. For SummitDev, it is primarily for doing things on the node that we have this machine for, because it's a relatively small machine. It has only 54 nodes. And for scalability, we're still using Titan, which has 18,000 nodes. Our user programs that eventually are going to use these resources consist of the ALCC, the Oscar Leadership Computing Challenge. This is for DOE mission driven research. And Insight. Insight gets about 60% of the resources. And this is for open science, and anyone in the world can apply for time. It's a once a year deadline for proposals. It's peer-reviewed, but it's open to anyone. As I said, we have a Center for Accelerated Application Readiness, and our goals here are to port applications so that they are ready to take advantage of our new architecture, so that the users that come into the user program, once we have Summit on the floor, have some applications that run very well, so that from day one we can do great science on that machine. That's one goal. The second goal is to develop experience with porting codes to that platform. So while we're working with application teams, we get a lot of experience and a lot of knowledge that we try to capture in a way that it can be advantageous for others later on who also want to port their code to this architecture. And then the third goal is to harden the system. So we want to both harden the software and the hardware by using science at scale on that machine. And this is part of the Center of Accelerated Application Readiness as well. It's what we call the early science phase of these projects. So we did a call for proposals for the Application Readiness Projects. And we did this 3 years ago. So we did a call for proposals, and out of the 29 applications that we got, we picked the following 13. And with these teams, we formed a partnership. It's staff at the OLCF, the developers of the code, and very importantly, also what we call the Center of Excellence of the vendors. So in this case, IBM and NVIDIA, and to some extent Mellanox, but primarily IBM and NVIDIA, are partnering with us on these CAAR applications to help them be ready for this next machine, because they know the software and they know the hardware. The application owners know actually the algorithms and the kind of science that you can do with it, and we are sort of sitting in the middle. We need to learn from both sides so that we can help others with it as well. We picked these applications in such a way that we have a large number of algorithms represented. We also have obviously the expertise in-house when it comes to the science is important. We cannot work with applications where we really don't know that much about. And then third, it's also to extract all this experience that others can then benefit from. So there's also a reason to have multiple algorithms represented. Now, I don't have time to go through all these 13 to tell you about what they're currently doing and what the status is of these projects. So I picked a few. One is a code called DIRAC. It's a relativistic electronic structure method. This is very important for heavy elements, including actinides, so plutonium, uranium, that type of metal. Understanding how we can produce better nuclear fuels would be an application, or how we deal with contaminated sites is another application. So doing relativistic electronic structure is an important DOE mission. We're looking here at the couple cluster method. This is a method that is built upon tensor algebra, and we are developing a library that runs very efficiently on these very large systems, that takes the complex algebra out of the hands of the developers, so that they can actually do the science, they can develop their methods, and as long as they can express this in terms of tensor algebra, this library will take care of doing that efficiently. So it consists of two pieces, TAL-SH. This is a device unified tensor algebra API. It does all the tensor algebra on the node, and it is very, very efficient. It has been written using CUDA for the GPUs, Intel TBB for the Intel mics, so it's also portable between different architectures, because that's very important for our users as well. And then it has this distributed data layer. So that's the layer that actually sits on top of it, that can distribute the tensors over the different nodes that we have. And this is almost finished, and this will be important for not just the DIRAC code, but for a lot of other electronic structure codes as well. So here's a little bit of a intermediate result. This is on a single node. So this is TAL-SH, that's that tensor part of this library that runs on a single node, looking at different sizes of the problem, and look at the calculated flop rate for this library on this particular problem, and then comparing that with straight DGEM and with the efficiency compared to the theoretical maximum. And so we get to 81% of a DGEM, so this is a simple case. There are other operations that are part of this library that DGEM would not be suitable for. And 66% of theoretical maximum. So this is a really good result on the K20s. And then we had access to a box with multiple K80s as GPUs to look at the scalability within the node. And if you look at adding more GPU units, we're actually just about linear in the scalability on the node. Another one is Flash. This is an adaptive mesh refinement code that is primarily used for astrophysics simulations. Bronson Messer, one of our staff members, is an astrophysicist, and he is using this for simulations of supernovae explosions. And he has been using SummitDev to look into using OpenMP 4.5 as an offload to the GPU, also using the combination of MPI for internode communication and OpenMP for intranode communication, and then on top of that using OpenACC. And he gets very, very good results with especially increasing size of his problem, where there's a significant performance improvement from using the GPUs, and these are the Pascals on SummitDev, as well as getting very good linear scaling with the number of with the number of ranks used. NAMD is a biomolecular simulation code. It's a very well-known code. It runs very well on GPUs already. And we have taken this on as an additional challenge to look at these kernels and rework those kernels to make them even more efficient. And the results of that work. Let me skip this slide. Are here. So this is comparing the state of the code that we had before we started with it, and it was already very, very efficient. This is a code very well known for its efficiency, and we reworked these kernels to make it even more efficient. And what is important to note here is that for the smaller systems, the smaller molecular systems, we actually got the largest improvement of the performance. And this is really, really important because codes like NAMD scale very, very well for very, very large systems. The strong scaling for smaller systems is where they lack. And so this is going to be really, really important to them. Another thing that for this particular project is noteworthy is that while we were doing this, the results of our work immediately was adopted and put in the repository so that anyone who is using NAMD anywhere on GPUs can already take advantage of the improvements that we made. And then this is an example of explicit solvent and implicit solvent, but that's more for the people who know this stuff. QM-CPAC, I think this is the last example that I have. This is a material science code. It's doing quantum Monte Carlo, so it's very well parallelizable. And here are some results. So comparing Titan with SummitDev. So this is a weak scaling problem. Seeing how many walkers in this Monte Carlo way of solving the problem you can run, and the timing is here. And the best timing for using the GPU on Titan is the second line. So having 40 walkers, having for this particular problem the execution time here. If you want to go up from that, you run into this memory problem. If you compare this with SummitDev, we can go all the way out to 1024 walkers. And of course that takes more time, but we now do, what is it? 25 times the number of walkers. And so we get an improvement in performance of close to 20, comparing running on the CPU on Titan and the CPU on SummitDev. So SummitDev has been an extremely valuable resource for us because we could start working on a system that has NVLink connected Power8' CPUs and the Pascal GPUs. And this is the best platform for us to start working towards Summit. A lot of applications felt immediately the performance improvement. Actually, there was one application that as soon as they got access to SummitDev, they ran their code, and in one afternoon they said, when do we get access to Summit? We're done with SummitDev. So not all of them were that lucky, though. Okay, so I'm talking about all of these. I'm not actually doing the work. It's all a lot of other people who actually do the work. So it's all the PIs and their teams on these CAAR applications. It is the scientific computing staff at Oak Ridge National Laboratory. And the postdocs, I should mention, we have a cadre of 10 postdocs that work with us. And then the Center of Excellence staff. And so with that, I would like to thank you for your attention. And if you have any questions now or maybe later, there's my email address.